By the end of this video, we will have made a bot that solves word search puzzles by itself. Enjoy! Welcome to this algorithms project. Today we will try to make a word search solver. Word search is a popular game that you probably played at least once during your lifetime. The concept is simple. We have a grid full of characters and we have a set of words that we need to find inside it. Here is an example of the game solved. The way words are positioned in the grid differs from a version to another, but in the popular version, a word comes as a straight line, whether from left to right, from right to left, from top to bottom, from bottom to top, from top right to bottom left, from bottom left to top right, from top left to bottom right, or from bottom right to top left. The important is that it comes as a straight line. Playing the game as a human is simple. It's just a matter of time before finding all the words. But what if we make a program to solve it? I think that it's interesting and a good practice on algorithms and data structures knowledge. Let's start. How is the input represented? We have a matrix of n rows and m columns of characters and a set of strings that represent words we need to find in the grid. And as output, we have many choices. We can, for example, have an array of moves we need to perform to win. A move is defined by the straight line we need to draw. We can store a starting and ending position in the grid. Here is an input-output example. Okay, but what about the instructions? Today we will see two solutions. The first one is quite obvious, the brute force one, to check every possible word in the grid in the 8 directions. And for each one of them, if it's in the set of words, then we found that word. We add a move and we remove the word from the set. This solution should be fine for small grids, ones that we usually play on a website or on a newspaper, of size 10 by 10 or 15 by 15 for example. But what if we had a 10,000s by 10,000s grid? There would be billions of words to traverse, very inefficient in terms of time. Let's dive a bit deeper into this solution to understand why it's inefficient. We can, for example, decide to traverse rows, then columns, and diagonals. We start with rows, we're at the first row, and we start from the first cell. We will now traverse all substrings that start from that cell, and check which ones are in words. We have A, AU, AUC, and so on. None of them was in words. But what do you notice? We can notice that we don't even have words that start with A. We traversed all the n substrings for nothing. We could avoid doing so since the beginning. We could start by making sure that we have at least one word that starts with A, which was not the case here. First deduction, we shouldn't start traversing from a cell if we don't have words that start with its letter. Okay, now let's suppose that this cell had the letter B instead of the letter A. We have words that start with B, we can start traversing substrings. We have this one, this one, this one, and so on. Once again, we didn't find any word. The reason behind it is that, even if we had words that start with B, but none of them had U as a second letter, so we traversed all these n-1 words for nothing. Second deduction, after choosing a cell to start from and a direction, we should first check that there exist words with the next letter from that direction as their second letter. Now let's suppose that we had E instead of U. Do we have words that start with B? Yes. We go to the right, for example. Do we have words whose second letter is E? Yes, we can keep searching. We traverse this substring, this one, and so on. Once again, unsuccessful search. Why? Because we have no words whose the third letter is C, so before traversing all the n-2 substrings, we could check if we had at least one word with C as a third letter. What do you notice? You can notice that traversing useless substrings is coming from the fact that we're not checking that there exists at least one word with that prefix. So what we can do is that we don't choose to start from a cell unless there are words that start with it. And if it's the case, when going from a direction, we don't continue unless there exists a word whose the ith letter is the ith letter of the word we're building. Let me show you an example to better understand. We start from the first cell of the first row. Do we have words that start with B? Yes, we can start from this cell. Let's go to the right. Do we have words with E as a second letter? Yes, we continue. Do we have words with C in the third position? No, we stop. We have no words with the letter of the next cell, so it's useless to continue from this direction. In our initial solution, we decided to start traversing rows in both directions, then columns in both directions, then diagonals in both directions. But what we can also do is that for each cell, we traverse all the 8 directions. We get the same result. So now we move to the next direction, bottom right. E as a second letter? Yes, we have. Words that start with B? No, we don't have. We stop. From the bottom now. Words that start with BY? No, we stop. All other directions go out of the grid. We try to start from another cell. Next cell, E. Do we have words that start with E? No, useless to start. Then we have C, and we have words that start with C. From the right, we don't have words that start with CK. From the bottom right, no words with CC as prefix. From the bottom, no CB. Bottom left, no CE. Left, no CE. All the directions go out of the grid. So we found no words from this cell. Next cell, K, no words. Next one, T, same thing. Then Y, same thing. Then E, same thing. Then X, same thing. Then B, we have. From the right, BN, we don't have, so we stop. Bottom right, no BM. Bottom, no BU. Bottom left, BE, we have, we continue. BEG, we don't have, we stop. Left, no BX. All the directions go out of the grid. You can see that even if we didn't find the word yet, but we avoided a lot of useless substrings. Next cell, N, no words. Next cell, Y, same thing. Then E, same thing. Then B, we have. From the right, no BC. Bottom right, no BI. Bottom, BE, we have. We continue from that direction. BEL, we have. Then BELO, we have. Then BELON, we have. Then belong, we have. And it's an actual word, so we finally found the word. Then belong you, we don't have, we stop. Bottom left, no BQ. Left, BE, we have. BEY, we don't have. Top left, BE, we have. But it goes out of the grid after it. Top, no BC. Top right, no BK. We traversed all directions of this cell, we move to the next one. And by doing this with other cells, we will necessarily find words we're searching for, if they're in the grid obviously, but just with reducing the amount of substrings to traverse. Let's try to write pseudocode for this solution. We know that we need to traverse all the cells, but we only deal with those with which we have words that start with the same letter. We write for each row I, for each column J, if there exists a word that starts with grade of ij, we can start working. If the condition is true, we traverse the 8 directions, top left, top right, right, bottom, bottom left, left. In any order, by the way, it doesn't really matter. And for each direction, we check that words we can find by going straight from there. Now question, to traverse a direction, will we use depth first search or not? Think about it for some seconds. And the answer is no, we don't need depth first search. Depth first search is used when we need to recursively traverse multiple directions, which is not the case here. It's true that for each cell we have 8 directions, but once we choose a direction, we walk straight, which can be done with a simple loop. We don't recursively check the 8 directions. Depth first could be helpful in a version of the game where a word doesn't necessarily come as a straight line in the grid. For example, in the word search lead codes problem. In that problem, we're asked to search for a word in a grid of letters. And it says that cells must be horizontally or vertically adjacent, not necessarily in a straight line. Here is an example. Here, we can use DFS. For each cell, we try the 4 directions. And for each direction, we try the 4 directions, and so on. 4 directions and not 8 because cells must be horizontally or vertically adjacent, not diagonally. This particular problem is covered in my 50 popular coding interview problems course, a course with hundreds of students that covers 50 diverse and interesting problems to increase your algorithms and data structures knowledge and prepare for interviews. Link is in the description. Let's go back to our problem. We now need a function check to move from a direction given the cell we start from. What does this function need to do? This function needs to keep walking from that direction as long as a certain condition is respected. But what condition? First, we need to still be in the grid, so I, the index of the row, must be between 0 inclusive and n exclusive, and j, the index of the column, must be between 0 inclusive and m exclusive. We also need to have at least one word that starts with the substring we traversed so far. For example, if we started from the cell 1, 2 and we decided to go to the bottom, and we're at the third iteration of the loop, then so far we traversed the substring BEL. We need to have at least one word that starts with BEL to continue. Otherwise, it's useless. If all these conditions are true, then we can move. We add the actual letter to the substring and we check if it matches a word. If there exists a word that is equal to substring, then congratulations, we found a word. For that, we need to add a move. A move is defined by the cell from where we started and the cell where we found the end of the word, the actual one, ij. We also need to delete the word we found from the set of words. After the condition block, we'll move to the next cell for the next iteration. Oh, by the way, we used variables that we didn't define. Direction and moves are passed as parameters. N and M represent the number of rows and columns respectively. Start I and start j are the initial value of I and j, the cell from where we started, and substring starts as an empty string. Okay, now we have our solution, but how to actually implement it? Especially the part where we check if we have words that start with the substring. Well, actually, we can implement it by just traversing all the words and checking if one of them starts with substring. But it's a bit inefficient. Doing it at each iteration, for each direction, for each cell is quite slow. A better alternative is by using the try data structure. I covered the try data structure in a previous video that I really recommend you to watch before continuing this one. In brief, the try is a tree data structure that is here to group strings with the same prefix. For example, if we have the words playing, player, and plastic, the longest common prefix is pla, so we will have a single branch for pla. Then from the A, we will have 3 children to continue remaining characters of the words. We can also see that playing and player also have y in common. We use a single node, no need to have y twice. Orange nodes represent nodes where there is an end of word. It means that the branch from root to that node gives the string we want to store. A slightly bigger example, with words we were searching for in our previous example. This is the try that we get. And we're using a try because it gives us the ability to directly access strings with a particular prefix. For example, if we want words that start with BELO, we just start from the root and move to B, then to E, then to L, then to O, then all the subtree contains only words that start with BELO, which are belong and below in this case. Also, we can directly know if we have words that start with a particular letter, just by checking if it's not in root's children. Here B is in root's children, so we have at least one word that starts with B, but A is not in root's children, we directly deduce that we have no words that start with A. And this operation is done in O of 1 in average, instead of traversing all the strings and checking their first character. Let's now work with our example but by using a try. We start at the first cell of the first row, it's a B. We check in root's children, do we have B? Yes, we can work with this cell. Let's go to the right, do we have E? Yes, E is in node's children. You can see that we're moving to the child node each time. After there is C, do we have C in node's children? No, it means that we have no words that start with BEC. We start from this direction. Next direction, bottom right. Do we have E? Yes. Then do we have E? No, we stop. Next direction, bottom. Do we have Y? No, we stop. Remaining directions go out of bounds. Next cell, E. Do we have E in root children? No, so we have no words that start with E. Basically, the same thing will happen with the example we've seen. The difference is that this time, we know how to quickly check if there are potential words or not, by using the try. For example, when we get to this cell and go to the bottom, we have B, E, L, O, and G is an orange node. It means that it's an end of word. We found a word. What do? We remove it from the try, add the move, and continue working. In brief, our solution builds a try, then traverses cells, and to check if there exist words that start with a letter, we just check if it's in root children. If it's the case, we traverse directions to check what words we found by continuing from there. And to check a direction, we start from the root of the try, and we keep checking if the next letter is in children of the actual node. If we find an end of word, we add the move and remove the word from the try. And if we go out of the grid or find a mismatch, we stop. Let's implement all of this. In our main solution function, we take as parameters the grid and the set of words. First step, we store grid's dimensions and we create an empty array moves where we'll store moves we do to win the game. It will be our output. Then we build the try by simply creating an empty try, then inserting each word. You can watch the try video to see how we insert words in a try. Now we can start traversing cells. For each row I, for each column j, we start by checking if we have words that start with grid of ij. How to do so? We just check if grid of ij is in children of the try. If it's the case, we traverse the 8 directions. But how is a direction represented? How can we actually traverse directions? A direction can simply be represented with the amount of change we apply to I and j, the index of row and column respectively. For example, going to the bottom means moving to the next row plus 1 and staying on the same column plus 0, so the direction is represented as 1, 0. Or going to the top right means moving to the previous row minus 1 and moving to the next column plus 1. We represent it then as minus 1, 1. So our 8 directions are 0, 1, right, 1, 1, bottom right, 1, 0, bottom, 1, minus 1, bottom left, 0, minus 1, left, minus 1, minus 1, top left, minus 1, 0, top, and minus 1, 1, top right. For each one of these directions, we call the function check to move in that direction, starting from the cell ij. But what does check function do? It takes as parameters the grid, the try, I and j, the coordinates of the starting cell. IDiff and JDiff represent the amount of change we talked about. For example, when going to the bottom, IDiff will be 1 and JDiff 0. Inside the function, we store grid's dimensions, we save initial value of I and j because we will need them later, and we create an empty string that represents the substring we will start traversing. We also need a node to traverse the try. It starts at the root. And now we have the loop. Remember that we have 3 conditions. I must be between 0 inclusive and n exclusive, j must be between 0 inclusive and m exclusive, and we must have at least one word that starts with substring. And how to check the last one? We just check if the next character, grid of ij, is in children of the actual node. Remember the last example. Inside the loop, we add the character to the substring, we found a new one, and we move to that node we found in children. This is why node becomes its child whose letter is grid of ij. Now that we went to the node, we check if it's an end of word. If it's the case, then substring is a word we were searching for and we found it. Congrats. What do? We delete it from the try and add the move. The move here is a tuple that contains the coordinates of the starting and ending cell. Starting cell is start I, start j, and ending cell is the actual one, where we found the last letter, the cell ij. After the condition block, we need to move to the next cell in that direction to try the next letter. For that we use IDiff and JDiff. We add IDiff to I and JDiff to j. And we got our check function. Back to the main solution function, after traversing all the cells, we just return the moves we found. And we got the moves we need to perform to win the game. We made a program that solves word search puzzles. I'm not claiming that it's the best solution, but it's my attempt to solve the problem. It remains a solution that is way better than the brute force one. Okay, but what can we do with it? Is it just another program that will stay on our computer? No, we can do something with it. Two of the things we can do with it are, first, an interface that lets the user enters the grid and the words, then the program gives the solution. It shows where are the words located in the grid. And second one, we can make a bot that actually plays on an existing word search game. The first suggestion can be a good project if you're learning web development, for example, but in this video we will go with the second one. We will search for a website to play the word search online, make a bot to enter the website, start a new game, read the grid, read the words, and solve the puzzle while really applying the moves on the screen, as if we're playing. For that, we will use the Selenium Python library. It will give us the ability to open a browser, go to websites, read elements, and applying actions like clicking. First of all, we need to create the driver. We use WebDriver to create a Chrome session, for example. Make sure to have your Chrome driver. We maximize the window and we put the link of the website we want to go to. The one we use for this video is a website where we can play word search. We can wait a little bit for the page to load. The web page starts like this. We're interested by the grid and the set of words to its right. We can see that it's a 15 by 15 grid, so we put n and m equal to 15. We create a grid of size 15 by 15 and we need to fill it with characters of the grid. But how to get the character at cell ij? For that, we first need to find the element in the web page, because yes, a web page is made of elements. By having a look at developer tools, we can see that cells are of type div, their class name is grid, grid cell 1L102, a bit weird, and each one has its position, row and column. So to find the cell position ij, we write find element by xpath, where the xpath is a div with parameters class equal to grid, grid cell 1L102, row equal to I, and col equal to j. We put its text in grid of ij. Now we need to read words. Words are in a word list whose the class is wordlist read da04. We also used find element. Now a single word is of type A, so we find all elements of type A in the word list. We put their text in a set, the set of words. Now we can start solving. We use almost the same function we created. One difference, when we find a word, we need to actually perform the move on the screen. So after adding the move and deleting the word from the try, we need to kinda drag and drop from the start cell to the end cell. The start cell is at index start I start j. We go find it the same way we did when initially reading cells. And the end cell is at index ij. We found the cell with row equal to I and col equal to j. Now that we have both of them, we create an action. We want it to drag and drop from start cell to end cell, and we perform it. That's it. Back to our main code, we just solve the puzzle by calling solve function with the grid and the words. And here is the result. We made a word search solver. We can even make it play endlessly. We use an infinite while loop, and after solving the puzzle, we get an alert that says if we want to play again. So after solving, we wait like 2 seconds, and we accept the alert to play again. Now it keeps playing and playing. We finished our project. I hope that you learned new things today. If you have other project ideas, you know what to do. Just leave a comment. And if you want to support the channel, you can like, subscribe, share, or buy one of my courses. See you in the next video.